All right, now we're going to touch on some of the big picture ideas of section 1.4. 1.4 is all about how not to do statistics. So, many studies are conducted and many conclusions are made. But there are occasions when the study is not conducted in the correct manner, or the conclusion is not correctly made from the data. There are many things that you should question when you read a study. There are many reasons for the study to have bias in it. Uh, Bias is where a study may have a certain slant or preference for a certain result. So, the following, we're going to look at some questions or some issues that you should consider to help determine if there is bias in a study. One of the first things that we should ask is who funded the study? Does the entity that sponsored the study stand to gain from it, either in terms of profit or notoriety? In this case, we should scrutinize the results to make sure they are sound. This doesn't automatically mean that the results are wrong, just that we should be critical of them. For instance, if a study says that genetically modified food is safe, but it's funded by a company that sells genetically modified food, there may be a bias. Again, that doesn't automatically make the study incorrect. It means that we should just look at it with more scrutiny. Some other examples are lurking or confounding variables. This is when you can't rule out the possibility that the observed effect is due to some other variable rather than the factor being studied. For example, you give fertilizer to some plants and no fertilizer to others, but the no fertilizer plants are also placed in a location that doesn't receive direct sunlight. In this case, you can't tell if the plants that received the fertilizer grew because of the sunlight or if they grew because of the fertilizer. We should try to design experiments with this in mind. We should try to eliminate the effects of confounding variables by controlling all other factors that we can when designing an experiment. Overgeneralization is when you do a study on one group and then you try to say that it works on all groups. For instance, doing a cancer treatment on rats. Just because the cancer treatment works on rats, this doesn't mean that you can generalize this and say that this works on humans as well. Right. Generalizations may also be if a medication was only tested on a certain ethnic group or a certain age group, or maybe medication was only tested on men and women. It can be difficult to just generalize and say like, okay, this medication works the same for everyone, right? There's no way to know unless you take a sample, a representative sample that includes all of these different groups, whether the medication works the same on everyone or how it affects everyone. The new FDA guidelines actually stress using individuals from different groups as a result. Cause and effect is another type of bias that we could have in our study, or another kind of error that we could make. This is where people decide that one variable causes the other because variables are related or correlated in some way. For example, there's a relationship between the number of people drowning at the beach and ice cream sales. Well, does the number of ice cream sales cause more people to drown, or do people drowning, does that cause more people to buy ice cream? Of course not, right? These things both increase whenever it's hot outside. We also have sampling error. A sampling error is the difference between the sample results and the true population results. This is unavoidable and results in the fact that samples are going to be different from one another. As an example, if you take a sample of 5 people's heights in your class, you'll get 5 different numbers. If you take another sample of 5 people's heights in your class, you'll get 5 numbers that are probably different from the first 5 numbers. We also have non-sampling error. This is where the sample is either collected poorly through a biased sample or through an error in measurements. We should take care to avoid this kind of error. Another big important idea here is that something can be statistically significant while not really meaning much in practice. For instance, if you find a new drug for high blood pressure that does technically reduce the blood pressure of patients, but not by much, then it might not be worth putting on the market. Because even though there's a statistically significant change, it doesn't mean that it's worth actually producing, right? It's not worth it to market if it causes only very small changes. Another example of statistically significant versus practical significance would be that, well, maybe the drug you discovered does significantly reduce blood pressure, but it has major side effects, or it's prohibitively expensive, right? In this case, it's still not practical to market this kind of drug, right? So we want to take into account both statistical and practical significance whenever we are looking at our data. Surveys also have their own areas of bias. A few of the issues with surveys actually come from the wording of the questions, the ordering of the questions, the manner the survey is conducted, and the response rate. So we have hidden bias. These are often called leading questions. So whenever you're asking a leading question, right, you're asking a question in a way that will make people respond a certain way. For instance, are you worried about the number of young people without jobs? Or do you think that there's a lack of discipline in our society? Whenever you ask a question like this, people sometimes feel pressured to say yes, right? You're really leading people to try to say yes whenever you ask a question in this way. So phrasing questions in a way that leads people to a certain answer should be avoided. You should always avoid asking questions like this. Another example of a hidden bias might be ordering the questions in a way where one question kind of builds on the previous question. For instance, asking someone, do you text and drive? And then immediately asking them, should there be a fine for texting and driving? By ordering the questions in this way, the person has personalized the question, which may affect how they answer this second question involving this fine, right? If someone says, yes, I do text and drive, then suddenly they're personalizing this question about should there be a fine for texting and driving, right? We also have a non-response bias. This is when you send out a survey, but not everyone returns the survey. A 30 to 50% response rate is pretty standard. Below that is considered really poor, and you would typically say that your results from the survey are not valid. It's always best to conduct surveys in person, but doing so is very time and cost consuming. Phones are the next best way to conduct surveys. Emails can actually be okay ways to conduct surveys, but physically mailing someone something typically doesn't work out. I guess except for the census, right? Physical mailings are typically undesired. They have very low response rates. Voluntary response is where people are asked to respond via phone, email, or online. The problem with voluntary response surveys is that only people who really care about the topics are going to respond. So note here that all studies do involve volunteers. But the difference between a voluntary response survey and a scientific study is that in a scientific study, the researchers ask the individuals to be involved, while in a voluntary response survey, the individuals become involved of their own choosing. So again, only people who really care about the issue are going to become involved in this case. Let's look at an example. Suppose a mathematics department at a community college would like to assess whether computer-based homework improves students' test scores. They use computer-based homework in one classroom with one teacher and traditional paper and pencil homework in a different classroom with a different teacher. The students using the computer-based homework had higher test scores. What's wrong with the experiment? Well, here, you don't know. Let's see. Let me make my font size larger here. You can't know if the better test scores are because of the teacher or because of the computer-based homework. Right. We can't necessarily say, because again these are two different teachers that we're looking at, what caused these higher test scores, right? A better design would be if we had the same teacher teach both classes. So in that case, the only difference between the two groups would be the homework method. Of course, there's still some variation between students, but using the same teacher will reduce any confounding variables that we can actually really control for. Next up, let's look at some of these cause and effect examples. Let's determine if one variable did cause the other, or did cause the change in the other variable. Cinnamon was given, not giving. Cinnamon was given to a group of people who have diabetes, and then their blood glucose levels were measured a time period later. All other factors for each person were kept the same. Their glucose levels went down. Did the cinnamon cause the reduction? Well, since this was the study where the use of cinnamon was controlled, and all other factors were kept constant from person to person, then any changes in glucose levels can be attributed to the use of cinnamon. Yes, all other factors were controlled. There's a link between spray-on tanning products and lung cancer. Does that mean spray-on tanning products cause lung cancer? Here, we don't really have a study, do we? We just have that there is a link between these. So there is no study controlling for the use of the tanning spray. So we cannot say that increased use causes lung cancer. We might say that there is a link. There could be a cause here, but you can't say for sure. Also, I'm not sure if this cinnamon thing is true. I don't recommend just trying this if you're. I don't recommend just experimenting on yourself if you're diabetic. Please don't. And a couple more examples. A researcher conducts a study on the use of ibuprofen on humans and finds that it's safe. Does this mean that all species can use ibuprofen? No. Some things are toxic to different species, right? For instance, you can't give chocolate to dogs or caffeine to dogs, right? No. In fact, ibuprofen is actually toxic to cats. You can't just generalize and say that, well, because it works on humans, it works on all species. And aspirin has been used for years to bring down fevers in humans. Originally, it was tested on white males between the age of 25 and 40 and found to be safe. Does this mean that we can just generalize and say that it's safe to give to everyone? Not necessarily, right? There are so many factors at play here. There's race, there's gender, there's age group, right? These are all factors that should be considered. We can't just generalize here. In fact, there's actually been a link between giving children under the age of 19, so I'm just going to say between giving children aspirin when they have a fever, and something called Ray's syndrome. Ray's syndrome is a rare but serious condition that causes swelling in the liver and brain. So there is a possible link here between giving children aspirin when they have a fever and Ray's syndrome. All right, and this is it for section 1.4.